Hi everyone, and welcome to this video. In this unit, we're going to look at graphs and the derivative, and in this section, we're going to look at increasing and decreasing functions. So we know that a function is increasing if it goes up from left to right. And you can see some increasing functions here. As you read the graph from left to right, you can notice that the graph is going up. So as x is increasing, y is also increasing. And a function is decreasing if it goes down from left to right. So you can see the bottom three graphs. As you go from left to right, as x is increasing, the y values are decreasing. So what are increasing and decreasing functions? So we're going to just say that f is a function defined on some interval. And then for any two numbers, x1 and x2 in that interval, so here's x1, here's x2, in that interval, f is increasing on the interval if f of x1 is less than f of x2 whenever x1 is less than x2. So pretend we had our x-axis right here, and let's pretend we have x1 is right here, x2 is right here, and we have some curve that maybe looks like this. Okay, right there is f of x1, so that's your y value when x is x1, and then here we have f of x2, which would be the y value for x2. And you can see here that anytime x1 is less than x2, f of x1 will also be less than f of x2. So we know that the function is increasing. So f is going to be decreasing on the interval if f of x2 is greater than f of x, if f of x1 is greater than f of x2. So you can see here, if I had my x-axis, and again, here's x1, here's x2, and let's say we had this time something like this. Here's f of x1, and here's f of x2. And you can see here that the value for x1, right, is greater than the value for x2. Okay, and of course that's whenever x1 is greater than x2. And then we also have constant functions. So f will be constant on that interval if f of x1 is equal to f of x2 for all x1 and x2, right? So we know that when you have a constant function, the y value is not changing. So here's x1, here's x2, and we would have maybe a horizontal line like this. And f of x1 is going to be the same value as f of x2. So therefore that tells us that the function is constant on that interval. Okay, let's look at an example. So here we need to find where the function in the figure to the right is increasing, where is it decreasing, and where is it constant. So let's talk about increasing first. So if I look at the graph, I know a function is increasing, right, when the graph is going upward from left to right, okay? And I also know that it's increasing when f of x1 is less than f of x2. So I can see right here that the graph is increasing, and I can also see right here that the graph is increasing. So what would those intervals be? This interval here would be from negative infinity and then to -4. So -4 right here, comma, whatever y value this is, that would be the inflection point. That's where the graph is changing direction. So we're going to use parentheses. We don't have a closed interval because right at that x value there, the graph is shifting and it's going from increasing to decreasing. So my first increasing interval is negative infinity to -4. And then also from +4 to 6. Notice that we're using the x values to describe intervals of increasing, decreasing, and constant. So that's very important when you're reporting those intervals to use x. So for decreasing, we can see right here that the graph is decreasing, and we can also see that the graph is increasing there between those two x values as well. So it's decreasing from -4 to 0, and then it remains constant, and then it's decreasing from 6 to positive infinity. And then constant is the horizontal line there, which goes from 0 to 4. Please pause the video and try the next problem on your own, and then you can unpause when you're ready to move on. How can we tell from the equation that defines a function where the graph increases and where it decreases without looking at the graph? The derivative actually will tell us that. So recall that the derivative of a function at a point gives the slope of the tangent line to the function at that point. And also remember that a line with a positive slope rises from left to right, and a line with a negative slope, of course, falls from left to right. So here's some tests we can use for intervals where f of x is increasing and decreasing without actually graphing. So suppose a function f has a derivative at each point in an open interval. If f prime of x is greater than 0, that tells us that f is going to be increasing on the interval. So it's going to be going up. If f prime of x is less than 0, f is going to be decreasing on the interval. So it's going to be pointing down. And then if f prime of x is equal to 0, f is constant. Okay, and of course, this last one must be true for the entire open interval, not just a point. So in order to determine all of this and to help us graph, a function, one of the keys that we use to graph is whether the function is increasing, decreasing, or constant. So the derivative is going to help us with that. In order to determine, where these functions increase, decrease, and are constant, we need to look what are called critical values. And the critical values are kind of like your boundaries. So the numbers C in the domain of f for which f prime of c equals 0 or f prime of c does not exist. Here's how we apply the test for increasing and decreasing. We're going to locate the critical numbers for f on a number line as well as any values where f is undefined. Okay, these values are going to determine several open intervals. Step 2 is we're going to choose a value of x in each of the intervals that we found in step 1. And we're going to use those values to determine whether f prime of x is greater than 0 or less than 0 in that interval. And then step 3, we're going to use the test above to determine whether f is increasing or decreasing on that interval. Let's take a look at an example. Find the intervals in which the following function is increasing or decreasing and graph the function. So one of the first things I need to do is find the derivative. And we know the derivative of x cubed plus 3x squared minus 9x plus 4 using the power rule is just going to be 3x squared plus 6x minus 9. Okay, so now what I want to do is determine where f prime of x is either equal to 0 or where it's undefined. So I'm going to take my derivative and set it equal to 0. And I can factor this. So first I would factor a 3 out and I'm left with x squared plus 2x minus 3 equals 0. And then I can factor my trinomial into x plus 3 times x minus 1. So I get these two values, negative 3 and 1, right after I set each of these quantities equal to 0. Okay, each of these is going to be a critical point. So I want you to visualize a number line. Here's negative 3, here's 1. Okay, they're my two critical values. I want to choose a number to the left of negative 3, so maybe negative 4. A number in between my two critical values, so 0 is an easy number. And then a number to the right of 1, which would be 2. And what I'm going to do is I'm going to plug those three numbers I just chose, negative 4, 0, and 2, into my derivative. So I'm going to plug it into this version here. And we're going to look at whether it gives us a positive number, a negative number, or 0. And we don't have to worry about where this function is undefined because it's a polynomial function and it will never be undefined. So now if I plug in negative 4 into this expression here, which by the way you can do on your graphing calculator if you want. You know how to use the table to do that. If I plug in a negative 4 here, I would get negative 1. And if I plug in a negative 4 here, I get negative 5. And a negative times a negative is a positive, times a positive stays positive. So that tells me that my derivative is positive. So that means the function, the f prime of x is greater than 0, which we learned means the graph is increasing. If I plug in 0, I get 3 and negative 1. So you have a positive times a negative. which is negative. So that tells me that my function is decreasing because my derivative is less than 0. And then if I plug in a 2, I get a positive 5, a positive 1, times a positive 3, so that's positive. So that means that it's going to be increasing there. So the sign of the derivative is in that bottom row, and this top row is telling us whether the function is increasing or decreasing. Now, to graph it, I want to take my values and plug them in to get some, corresponding y values. So if I plug in -3, my critical value, into my original expression, this would give me -27 plus 27, which is 0. And then I have 27 plus 4, so that's 31. I also want to plug in 1, my other critical value. And that would give me 1 plus 3, which is 4, minus 9 is -5, plus 4 is -1. And then I'm also going to plug in -4, 0, and 2. So that's why it would be helpful to have have this on your calculator. But when you plug -4 into this expression, you're going to get 24. And when I plug in 0, I get 4. And when I plug in 2, I get 6. Okay. So I've got all these points. And I'm going to have to be careful how I label my axes. So for the x-axis, I can just count by 1s, but maybe the y-axis I'm going to count by 4s because my highest y value is 31. Okay. So I'm going to graph these, -3, 31. So -3 is here, and then we're going to count by 4s, right? So 4, 8, 12, 16, 20, 24, 28, 32. We need to go to 31, so it's going to go like right about there. Okay. And then I've got 1, -1. So that's going to kind of go right about there. -4, 24. 0, 4. And 2, 6. Okay, now we're going to use this piece here to figure out the direction that the graph is going to go, right? Because we know it's increasing and decreasing. So where is it increasing at? Well, in two places. On the interval from -infinity to -3, and then on the interval from 1 to infinity, right? So I know that it's increasing from -infinity to -3, and then 1 to infinity. Okay? So I know that somewhere from here to here, it's increasing. And then somewhere from here to here, it's also increasing. So my graph's going to kind of follow this. Now it's decreasing from -3 to 1. So I know that the graph is going to be decreasing in here, right? So I can connect it now. And that is a rough shape of what your graph would look like. You can try pausing the video and then practice the next problem on your own, and then unpause when you're ready to go over it. Okay, we're going to look at example number 3 next. So we want to find the critical numbers and decide where f is increasing and decreasing. And you don't really have to graph it. You can check the graph on your calculator if you want. So in order to find increasing and decreasing and critical numbers, I need to find the derivative, right? And to find the derivative, I need to use the chain rule. So I'm going to have 2/3 times x minus 1 to the 2/3 take away 1 would give me negative 1/3, and then times the derivative of this quantity, which would just be 1. So I don't really need to put that. I'm just going to rewrite this as 2/3 times x minus 1 to the 1/3 power. Okay, so now to find the critical values, I need to find where the derivative equals 0. Well, if you think about this, it'll never equal 0 because my numerator is a 2. So what I want to do instead is find where the expression would be undefined. So you're dealing with a rational expression, right, that has a radical built in. And we know that we don't want the denominator to ever be 0. So that just means that I want to take the denominator and set it equal to 0 to find the value that would cause the function to be undefined. So I'm going to take 3 times x minus 1 to the 1/3 power and set it equal to 0 and solve for x. So I would divide both sides by 3. I would get x minus 1 to the 1/3 equals 0. And then I want to undo that 1/3 so I can cube both sides. So now it would just be x minus 1 equals 0. So x equals 1. Okay, now one of the things I want to ask myself is just because I get this value doesn't mean it's a critical value. I know this is critical though because it's in the domain of f, right? So if you look at f here, this is a cubed root. You can take a cubed root of 1, you could take a cubed root of 0, you could take a cubed root of a negative. If I plug 1 in here, it gives me 0, and you can take the cubed root of 0. So this value is in the domain of that. So therefore, it's a critical value, okay, because it's in the domain of your original function, but it makes f prime undefined. If I was to plug a 1 in here, you would get 0, and 0 times anything is 0, right? And 2 divided by 0 is undefined. So that means it's critical. So you only have one critical value. Okay, so we're just going to throw a 1 on there. I'm going to pick a number to the left of it, like 0 is a good number, and then pick a number to the right of it. And I'm going to take those values, the 0 and the 2, and plug them into my derivative. So I'm plugging them into here. And remember, I don't care about the actual number, I just want the sign. So if I plug in a 0 here, 0 minus 1 is negative 1. The cubed root of negative 1 is negative 1. And a negative times a positive is a negative. So this is going to be negative right here. Okay, the derivative's negative. That tells me that the function is decreasing. When I plug in a 2 minus a 1 gives me a positive 1. And if you take the cubed root of a positive, you get a positive. So that tells me that it's a positive times a positive, which is a positive. So that tells me that the function's increasing. So I know it's decreasing from negative infinity to 1, and it's increasing from 1 to infinity. Okay, and we don't have to graph that by hand. But if we were to graph it on Desmos, you'll see. So if I type in my original function, x minus 1, and then to the 2/3 power, okay, you can see here that the graph hits the x-axis at 1, right? You can see if you read the graph from left to right, from negative infinity to 1, the graph is decreasing, as we said, and then from 1 to positive infinity, the graph is increasing. Please pause the video and try the next check your understanding on your own, and then you can unpause when you're ready to move on. In my next example, I need to find the intervals for which the following function increases and decreases, and then we'll also graph it. So here we have a rational function, f of x equals x minus 1 over x plus 1. So we also have a quotient. So to find the derivative, I know that I need to use the quotient rule, right? So u is just going to be my numerator, x minus 1, and v will be my denominator, x plus 1. So the derivative of x minus 1 we know is just 1, and the derivative of x plus 1 is also 1. Okay, so now I need to use my quotient rule. So it's just going to be u prime times v, so that would be 1 times x plus 1 minus v prime times u. And then all over v squared. So if I clean up the top part, I end up with x plus 1 minus x plus 1. And the x's are just going to disappear. And you would get 1 plus 1, so you get 2 over x plus 1 squared. Again, we want to set this equal to 0, but it's never going to equal 0 because my numerator is a 2. So instead, I'm going to find where the derivative is undefined, and that would be in the denominator. So I want to take the denominator and set it equal to 0. And if I was to solve this, right, there's a couple ways you could do it. Take the square root of both sides, and you get x plus 1 equals 0. So x would equal negative 1, okay? Now negative 1, though, is not a critical value. Why? Because if I take negative 1 and plug it into my original function, it's not in the domain, right? It would make it undefined. So negative 1 is not a critical value. However, we can still use it to determine where the function's increasing and decreasing. So take negative 1 and place it on your number line. Pick a number to the right, pick a number to the left. Just remember negative 1's not critical. Okay, so I'm just going to plug in some values here, right? And we're plugging them into our derivative. So if I plug in a negative 2, any number you plug in here and you square it, it's always going to be positive, so you end up with a positive. And then if I take 0 and plug it in, again, you get a positive. So the function's increasing from negative infinity to positive infinity. Okay, now with rational functions, remember, I need to look for asymptotes, right? So we got to find some asymptotes here. So if I look at my original function, right, to find the vertical asymptote, you set the denominator equal to 0. So I know I'm going to have a vertical asymptote here at x equals negative 1. And then to find a horizontal asymptote, remember, you look at the powers. And here the powers are the same. They're both 1. So you take the coefficients and divide them. So 1 divided by 1 is 1. So my horizontal asymptote is just y equals 1. So it's going to look like that. Okay. Now to graph this, I'm going to take negative 2, plug it in, take 0, plug it in, see what we get. So if I plug in negative 2 minus 1 is negative 3. Negative 2 plus 1 is negative 1. Negative 3 divided by negative 1 is positive 3. So f of negative 2 is positive 3. I'm also going to plug in 0. So that would give me negative 1 over 1, which is negative 1. So one of my points is going to be negative 2, 3. and the graph is just going to kind of follow the asymptotes. My other point is 0, -1. So again, it's just going to follow the asymptotes and look something like that. Okay, please pause the video, and for the next two, you want to find the intervals on which the functions increase and decrease. In our last example, we have an application. A company selling computers finds that the average cost per computer decreases linearly with the number sold monthly, decreasing from $1,000 when none are sold to $800 when 1,000 are sold. Find the average cost function, C bar of x, where x is the number of computers sold monthly. Okay, so we know that when no computers are sold, we have $1,000, and when 1,000 are sold, we have $800. So I want to find linear, right? So I need to find the slope. So that's just going to be change in y over change in x. So I would have 800 minus 1,000 over 1,000 minus 0. And you end up with negative 0.2. Okay, so I can write this in slope-intercept form, right? Because I have the slope and I have the intercept. And remember that this is only from when 0 to 1,000 items are sold. Now to find the cost function, right, we know C bar of x, the average cost, is just C of x divided by x. Or you can think of it like this. If I want to solve for this, right, I'll just multiply both sides by x, and I get C of x equals x times C bar of x. So that's just going to be x times C bar, which we found in the last part. And then that's just going to be negative 0.2 x squared plus 1,000x. Okay, and again, that's when you sell from 0 to 1,000 computers. Now, suppose the revenue function can be approximated by this expression. R of x equals 0.0008x cubed minus 2.4x squared plus 2400x, where the number of computers you sell is between 0 and 1,000. Okay, so I know that profit is just going to be revenue minus cost. And I have both the revenue function and I have my cost function. So all I'm going to do is just subtract the two. I'm going to have this minus cost and I end up with my profit equation. Let's see, we can combine the 2x squareds and then the 2x's. So there's my profit equation. Okay, now what I'm actually doing here, which I didn't write down, the rest of the question is determine any intervals on which the profit is increasing or decreasing? So what do you think I need to find? If you said derivative, you are correct, right? I need to find the derivative. Okay, so to find the derivative of my profit function, we're going to just use our power rule. Okay, so we would end up with the following. And we want to set that equal to 0. Now to solve it, you need to use the quadratic formula. So you would have something like this. And when you solve it, you end up with the following two values, 409.8 and 1423.56. Now this value here is bad because it's outside the domain, right? The function only works when you sell between 0 to 1,000. So we can't use that value. This is the only critical value. So here I'm going to take my critical value and then pick a number before 409.8, like 0 is a good one, and pick a number after, we'll pick 1,000. If I plug in 0 into my derivative, so plug in 0 into this function here, you end up with a positive, so that means it's going to increase from negative infinity to 409.8, and then plug in 1,000 into my derivative, and you end up with a negative, so that means it's going to decrease on the interval from 409.8 to positive infinity. Okay. And that's all you have to do there. So when no computers are sold, the profit is increasing at a rate of $1,400 per computer, right? If I plug in zeros for my X's. And when 1,000 computers are sold, if you were to plug 1,000 in, you would end up with a negative 600. So that means the profit is decreasing at a rate of $600 per computer. So again, it's increasing from negative infinity, or actually 0, right? Because negative infinity is not in our domain. So from 0 to 409.8, and then it would be decreasing from 409.8 to 1,000. Okay, so the profit increases when 409 computers are sold and decreases when 410 or more are sold. And that's it for our video. If you have any questions, please reach out to me. Enjoy the rest of your day.